xn. Then why?
Mathematics made easy, no more fear. Target online class, we got you. Wherever you want it from, we got what you need. Target online class.
Good day, viewers all over the world. We are still continuing our concept integration. So we have been able to introduce integration. We know the meaning of integration. We know that when we have a derivative, dy dx is equal to xn, then the integral of this will be xn, which is f of x dx. And if you find this, it's going to give us xn plus 1 all over n plus 1 plus arbitrary constant. So we have been able to establish the fact that whenever you integrate a function, you add an arbitrary constant to that function. Whenever you integrate a function, you add an arbitrary constant to that function. So there are two types of integration. We have the indefinite integral. Under the indefinite integral, the integrand is open-ended. That is, let's say integral 2x dx. In this case now, if you have integral 2x dx, it has no bound. It's open-ended. It has no bound. If I integrate this, for instance, I'm going to have 2x. That will be x. You know, there's one there. Say 1 plus 1 all over 1 plus 1. 1 plus 1. That's what we're going to have. Whatever we have at the power, we are going to replace it at the denominator plus arbitrary constant. That's how to integrate. Then in this case, I'm going to have 2x squared all over 2 plus arbitrary constant. These two, we cancel these two. So the final answer will be s squared plus c. That is what we are going to get. So this is example under indefinite integral, where the integrand is open-ended. No boundary, is open-ended. Whenever you integrate indefinite integral, you must put arbitrary constant. It's a must. Because with this arbitrary constant, if you have subsidiary conditions, that can actually give us an idea of what it becomes. So when you have indefinite integral, there must be arbitrary constant. Then the second type of integration that we have is definite integral. Under the definite integral, we have the bound. There's a boundary. Say, for instance, let me use the general form now. If you have integral f of x dx, a, b, this a is the lower bound, while a is the upper bound. So this is example under definite integral. Then what is the implication of this definite integral? Normally, under definite integral, we don't need to put arbitrary constants. Why? Because it's going to cancel out. Let's see. If I have f of x, so if I integrate f of x dx, if I integrate this, I'm going to get f of x plus arbitrary constant. This is what I'm going to get. Then we put the bound a to b. That's the bound. So we are going to substitute this upper bound and this is the lower bound. From there now, that is, we substitute for x when x equal to b minus when x equal to a. That's the implication of this upper and lower bound. So I'm going to have f of x. That is, if I substitute for b, I have f of b plus c minus f of a plus c. That's what I'm going to have. Of course, minus will control everything there. Then at the end of the day, I will have f of b plus c minus f of a minus c. This c will take care of this c. At the end of the day, we are going to have f of b minus f of a. You realize that the arbitrary constant will cancel out under the definite integral. So when we have definite integral, we don't need to bother ourselves with the arbitrary constant. Just go ahead and integrate, because the arbitrary constant will actually cancel out along the line. But if what you are given is indefinite integral, is a must to put arbitrary constant. So that is what I'm trying to talk about. So we should note that. Then I'm going to give us a table. There's this standard table. We can get this table from any standard textbook. This standard integral table. That is, this will just show us what we are going to get. If you have integral of a particular function, then this is what you are supposed to get. As I'm going to show us this table. If you have a function f of x, then what will be the integral? Integral f of x dx. That's the meaning of this table. The first one, if you have a x raised power n, then if you integrate this, a is a constant. We have a x n plus 1 all over n plus 1 plus arbitrary constant. That is the first one. Then the second one, if we have f of x to be cos x, then what is the What is the integral of cos x sin x plus c? The third one, if you have sin x, these are trigonometrical functions. Sin x, it will be minus cos x. And you know, of course, this is the reverse of what we have under differentiation. Okay. Then here, if you have sec square x, if you have sec square x, then we are going to have tan x. Tan x. Of course, we can prove all this. Then the fifth one, if you have cosec, if you have cosec square x, if you have cosec square x, what are we going to get as the integral? It will be minus cot x plus arbitrary constant. Then the sixth one, if you have sec x tan x, if you have sec x tan x, it will be sec x plus arbitrary constant. Then the seventh one, if you have cosec x cot x, we are going to have minus cosec x plus arbitrary constant. Then number 8, if you have integration exponential function, it will be exponential function plus arbitrary constant. And lastly, the last one is that when you have 1 over x, then if you have the integral of 1 over x, will be in x plus c. So these are what you can get under standard table. That's what you get under standard table. So this is what you are going to get under standard table. So this is what you are going to get under standard table. We should try and note all this. So in our next class, we are going to divide integration into different type of integration that we have. Definite integral. We divide it into the way we take differentiation. That is, we take different type of integration that we have. So that's what we are going to do in our next class. We take different type of integration. We talk about integration of polynomial functions. We talk about integration by parts. We have integration by parts. We have integration by partial fraction, integration by substitution. We are going to break everything down. We'll be taking it one after the other. But this is just introduction to integration. This is just introduction to integration. And that's what we have. That's our target for tonight. So thank you for listening, and God bless you all.